Hello, I am Rui Cardoso, Senior Lecturer for Aerospace Engineering. This face you are seeing there is my face, and I'm going to introduce you to statics. So I'm going to show you some sample lectures and tutorials on statics. So if you want, for some reason, to email me with any query, you have my email address here. You also have these Instagram, Snapchats, Facebook, Twitter, things for Brunel, which you can try to follow. So what I'm going to cover in these sample lectures and tutorials is basically material for your year 1 at Brunel. So I'm going to cover statics only. Of course, you are going to do many other things, but the main topics I would like you to focus is basically the first 3: vector analysis. I'm going to give a very quick review of vector analysis with the basics. And then I'm going to move to equilibrium of a particle, where a lot of vector analysis is required. Then I will introduce moment produced by a force vector. So these are quite basic but extremely important concepts that you need to know very well for the remaining of your lectures. Then I will move to the equivalent system force moment, where you will learn how to basically build an equivalent system that is in the same equilibrium conditions as the original system. That will be very important for the topic that follows, which is equilibrium of rigid bodies, which is the main topic in statics. We will study many different types of supports. The bodies, or the rigid bodies, they need to have supports. They cannot be levitating in the air. And then we are going to learn how to replace those supports with forces, which are called reactions. And we are going to learn how to derive the equilibrium equations. Basically, these equilibrium equations will make sure that your body is in equilibrium. And then from those equilibrium equations, you can calculate many different unknowns. Then we will talk a little bit about beams. We will derive the transverse shear force and bending moment diagrams for beams. So this is a kind of introductory video I will have for all these sample lectures. Of course, different lectures will have this same introductory video, but they will refer to different topics on this table of contents if you want. Another thing you can, if you are more curious, I have a YouTube channel which you can, if you are interested, of course, and curious, you can try to see what I have there. So I have a lot of lectures in that YouTube channel, so you can search for that channel by googling Rui Cardoso YouTube. I have lectures for more advanced years, so I recommend at this point you not to see those lectures. But I also have some supporting material for statics in year 1 there in the YouTube channel. So I think is a nice thing for you to see as well. I would like also to say that all the examples I will be doing in these lectures and tutorials, not all of them, but many of them were taken from these recommended books I have listed here in this slide. So Engineering Mechanics Statics from Ibler, or from Vector Mechanics for Engineers, Statics from Beer and Johnson, from Engineering Mechanics Statics from Marian, Bolton and Craig, and also from my own book, Stress Analysis for Lightweight Structures, a MATLAB-oriented approach. So all the examples you will see in the videos, sometimes I refer which book I've taken the example, sometimes I don't, but these are the books that I follow. So in case I forget to mention which book I took the example, you have here the list of books, so you know where they came from. Right, thank you. So we will move now to the specific lecture. Okay, so for today, so we have only 1 hour or less than that. I will say 45 minutes. I propose to do this example from a past year exam. Last Monday I also solved a past year exam, a different year. Alright, so let's look at this problem. So what you have here is a press. So this press is basically exerting a force in this piece of wood, in this brick of wood, if you want. A force of 1.2 kilonewtons, as you can see there. Okay? So the press is locked. So it means when you, in order to lock the press, you need to push this link, which I think is called here the link CF, yeah? So that it becomes in contact with this structure here that I'm underlining in red at this point, which is point G, right? So you exert a force there in that link so that it will contact that point G, and then the press will be locked in that position. And in that case, you will have a force of 1.2 kilonewtons applied at point A in this brick made of wood. Okay? So the question basically is, what is the force P that you need to apply? We are looking for this force P in order to unlock this press. Yeah? Or to release the press. It's written there in the question. And an hint is given to you, which is a very important hint. In order to release the press, the contact force at G must be equal to 0. So basically, what it means is, when you apply this force P here, that link CF is going to move upwards, and then the contact at point G will not happen anymore. So the contact force at G is going to be equal to 0, or no contact force, right? Okay, so as we have seen last week, I think not last week, 2 weeks ago, last week you had a break, right, in the teaching, yeah? So 2 weeks ago, as we have seen, we learned how to do the free body diagrams. So I'm going to copy this figure to a different slide. So we learned last week how to do the free body diagrams. Remember? FBD, free body diagrams, where I told you that, for example, if you look at this figure there, you have many different parts. Yeah? For example, you have this part here, all of it. I'm underlining in red. Yeah? This part is connected to this link CF, which will be a link something like this. I'm underlining now in blue. So it is connected to this link CF at this hinge at point C. Yeah, this hinge here at point C. You see? And then you have another link or another part, which is this one DE. You see? I'm underlining now in black. Or you can have the whole thing. You can have another free body diagram that can be all thing connected, right? So we have here many options to build our free body diagram. And this is a key thing in this kind of problems. Look at the question in the exam. Here at the end in the exam, I gave you the marking scheme the construction of the free body diagram is 25% of this question. So we really value these free body diagrams, and we want you to construct the free body diagrams. The question here is, which part am I going to choose for my free body diagram? Am I going to choose the part in red, the part in blue, the part in black, or the entire thing? So we need to decide which part we are going to use. Okay? For example, if you decide to go for the part in red, this one there, so in order to build the free body diagram, we need to isolate this part for the rest of the press or the rest of the mechanism. So I need to break up the connections of this part with the rest of the entire system we have here. For example, if I look at point A, I know that I have a force of 1.2 kilonewtons applied at point A. So I need to keep this force, 1.2 kilonewtons. If I want to isolate this part, what do I have to do? Which connection do I need to break up? C and B. Yeah, very good. So I have this hinge here at C and this hinge at B. So if I want to isolate this part in red, I need to break up the connection at these two hinges. So whenever I break up a connection, what do I have to do? So whenever I remove a support or a connection, I replace that support with what? With reactions, right? So I need to put reactions at point C and B. Now look at this. Point C and B, they are hinges. If I try to move point C in the horizontal direction, do you think that hinge will allow that movement or not? No. So what this means what? If that movement is not allowed, there is a constraint or a force there or a reaction that is blocking that movement, and I need to include that reaction. I will call that reaction Cx. By the way, we need to have a coordinate system, right? So let's say this is my x-axis, this is my y-axis, with origin at point C. You can put the origin at any point, it doesn't matter. We can do the same way of thinking for if I try to move point C in the vertical direction. That hinge will not allow that movement, right? So if it does not allow, I also need to include a reaction in that direction, Cy. Yeah? What about rotation? If I want to rotate this part about hinge C, that rotation is allowed or not? What do you think? It is, right? Otherwise this will not be an hinge. Yeah? So rotation is allowed, so it means whenever the movement or the motion is allowed, we do not include a reaction there. In that case, that reaction will be a moment, but because rotation is allowed, we don't have a moment as reaction. So these are the only two reactions we will have at point C. Yeah? You all agree with this or not? Any questions on this? So can we assume that the same thing will happen at point B? It is also an hinge. So rotation about B is also possible, so no moment as reaction. So I can also assume that I will have a horizontal reaction at B, I will call it Bx, and a vertical reaction at B, which I will call it By. Okay? So in fact, what I should be doing because this figure is starting to become a bit confusing, so I'm going to do this. I'm going to copy it here. and I will get only this. Yeah? I think is more clear now. So this is our point C. This is our point B. This is the part of that mechanism that I isolated. And in order to isolate, I break up the connections at C and B. I replace that connections with the reactions. Of course, I need to include also the external force, or the force applied in this case by the brick of wood on the press. And this is my free body diagram, FBD. Yeah? So the next step is to build the equivalent system force moment, which you have been doing in the team-based learning sessions, right? So in the team-based learning sessions, you have been working on the equivalent system force moment. I can write here, equivalent system force moment. So basically what you do is you do summation of forces. You get the resultant of the forces, which is the summation of forces that you have. And you calculate also a moment about any point you want. This is a two-dimensional problem, so you will have only a moment component, one moment component in the z direction. So, for example, if you calculate the moments about point B, so this resultant of forces will give you a force vector with two components, summation of forces in the x direction, summation of forces in the y direction, yeah? While the moment equation will give you only one additional equation. So these are your equilibrium equations, and what we say is summation of forces, they need, in order to be in equilibrium, they need to be equal to 0. Yeah? And the summation of all moments about point B, they also need to be equal to 0 to be in equilibrium. Right? So, and that's all we have to do for these two equations, so we can continue here. So, which components do we have in the horizontal direction? You tell me? Cx and Bx. Anything else? That's it, right? What about the vertical direction? Yeah. Cy, By, and anything else? And 1.2, right? Plus 1.2. And this needs to be equal to 0. So this will give me two equations. So I underline it in blue there. I will get two equations. The first one is Cx plus Bx equal to 0. The second equilibrium equation is Cy plus By plus 1.2 equal to 0. Yeah? We need to work out now the moments equation. Summation of moments about point B equal to 0. So we will have, which moments do we have about point B? So I will start to make this question. Let's start with Bx. Do you think Bx produces any moment about point B? Why not? It passes on point B, right? What about By? Same thing, passes on point B. What about Cy? This figure might not be clear, but you can see from this one that the force, the reaction Cy, if you extend, is also passing on point B. So the distance in the perpendicular direction to Cy is 0, right? This means the moment produced by Cy is also 0. What about Cx? Yes. So that moment is clockwise or anti-clockwise? Clockwise. So it should be positive or negative? Why positive?
look at this. You are seeing the x-axis, right? Look at 4 fingers of my hand. I'm aligning 4 fingers in the horizontal direction with my x-axis, okay? I will rotate my fingers towards my y-axis, like this. My thumb is in this direction, right? You agree with me? Yeah. This direction is the positive z direction. So when I rotate my fingers anti-clockwise, I get positive z, isn't it? So if a moment tends to rotate anti-clockwise, that moment should be positive. Okay? In this case, Cx will tend to rotate this part about point B in a clockwise direction. So that moment should be negative, so minus. Now, in order to have the moment, I need to multiply the force, which is Cx, by the distance in the perpendicular direction. I think this figure for the distance is better. Which distance do I need? Well, 24 millimeters, that's right. So is basically when you start from point B, I need to get this distance in the perpendicular direction to the force, Cx, yeah? So this distance is 24 millimeters, okay? Everybody got that or not? So I multiply this by 24. What about this 1.2 kilonewtons? First thing, the moment will be clockwise or anti-clockwise about point B. Clockwise, so also negative. The force is 1.2. So we are working with kilonewtons for the force, is okay. Now the distance I need is this one from point B all the way to the force in the perpendicular direction, right? So I need to have this distance here, which is 66, right? Agree? So it's not difficult, is it? So times 66, that will give me a moment. Sorry? What about units? Well, we are working, for the force we are working in kilonewtons. For the distance we are working in millimeters. So the units we're going to be kilonewton millimeters. For the moment, yeah? Yeah, it's okay if you leave it at that, as far as you don't mix millimeters with meters. If you work with millimeters, you need to, everything needs to be in millimeters. If you want to work in meters, everything needs to be in meters, yeah?
But if you work in newtons and meters?
Yes, fine, it's perfectly fine.
So in an example, that is still work with SI?
SI, yeah. Yeah.
So
Yeah, SI, yeah. Kilonewton millimeters is also SI.
yeah, it's SI, but like
Yeah. Yeah, it's perfectly fine. Okay? Yeah. All right, so this is our additional equation. And now we need to look at, so these are the 3 equilibrium equations we have. And now we need to look the number of unknowns that we have. So let's see. We have Bx, By, Cx, Cy, right? These are the reactions we don't know. So we have 4 unknowns for 3 equilibrium equations, which means we don't have enough equilibrium equations for our unknowns. So we have to do something more. Yes?
With the moment around C also helps work out Bx and Cy. Yeah.
No, we are calculating the moments about B, not about C.
I mean, if you fit C without
Yeah, if you calculate about C, of course, you need to then, the Cx and Cy don't produce any moment about C. By will not produce any moment about C. You will have to calculate the moment produced by Bx about C. But in our example, we are calculating moments about B. Yeah? All right, so we don't have enough equilibrium equations. So what you have to do if this happens is you need to get another component. You need to do the free body diagram for another component of your mechanism. And the other component you can do is the link CF, for example. So I'm going to use this figure here, and I'm going to do it in blue now. I'm going to underline the link CF. Okay? So you need now to isolate this link CF in blue. I underlined in blue. And then you, in order to isolate, you need to break up all the connections of this link CF. So what I can do, because this is getting a bit more complicated, this drawing, I can do the same what I did before. So I can try copy, paste, and now I can get rid of this one. Okay, so look at this. I'm going to isolate this one in blue. I'm going to delete this one in red now, because the one I'm isolating is the one in blue. So these reactions Bx and By, they belong to the part in red, so they don't belong to this part in blue. Okay. I'm going to leave for now these two reactions Cx and Cy in red. Don't forget, these Cx and Cy in red are the reactions on the part that we isolated that was in red color, right? But now we also have the same point C for this part in blue. So basically this Cx and Cy in red that you have there was the action of this part in blue into the part in red. What is going to happen? Newton's third law, the part in red will react on the part in blue with the same reactions at C, but in the opposite direction. So this is going to be my Cx, and this is going to be my Cy for my part in blue. As you can see, they have the same magnitude, Cx and Cy, but the direction is symmetric, is opposite, right? And then, of course, this Cx and Cy in red, they don't belong to this body. They belong to the body in red. So I'm going to get rid of this Cx and Cy reactions there. This is extremely important. This is the most important thing in this example. This is Newton's third law. For every action, there is a reaction. Look at this. Look at my action on this column. I'm doing a force to the left, to this column. The column will react in my hand with a force with the same magnitude, but to the right. So my hand is in equilibrium, is at rest. Yeah? So you need to do exactly the same thing here. So compare these two things. Look at Cx and Cy for this body in red. Cx to the right, Cy upwards. And now this one in blue, you have Cx to the left, Cy downwards. Yeah? The other way around, exactly. Before we there are still other forces we need to include here. Which forces do we need to include more? So in order to isolate this body in blue, so I break up the connection at C. I put there my reactions already. That is done. What other connection do I have to break up in order to isolate this body in blue? D. So I need to include a reaction at point D. So my point D is here. So do you think I need to do something like this? dx, dy at point D?
Yeah.
You can do this, but you will be in trouble. You can do, is an inch, you can do this, but you will be in trouble. And the reason is you still not get enough equilibrium equations for your solutions. So what I want to emphasize here, before we put these reactions at point D, I want you to look carefully to this strut DE, this one in black. Let's look at this strut DE, okay? I'm going to put this strut DE. I'm going to put it here. So this is my point D, this is my point E. This is my strut DE. Strut DE needs to have the force. Okay, I don't know if I did this Monday or on a Thursday lecture, but I'm going to do it again. So imagine a strut DE like this. This is point D, this is point E. Okay? So these are hinges. So let's assume we will have these two reactions at point E. So our EX and our EY. So let's also assume that the strut is aligned with my x-axis, okay? Let's assume I will also have a dx and a dy. All right? What I'm going to do now is this. We know one of the equilibrium equation is summation of moments about a point D, for example, needs to be equal to 0 for this strut to be in equilibrium. Okay? dy and dx, they don't produce any moment about D. You all agree? Yeah. What about Ex? Does it produce any moment about point D? No. The Ex is also passing on point D, right? So the only force here producing moments about point D is force Ey. And that moment is going to be equal to the force Ey times this distance, right? Which is the length of my strut. I will call it L, for example. So if I multiply Ey by L, this is the moment produced by Ey, and this moment needs to be equal to 0 so that the strut is in equilibrium. Yeah? Look at this now. I have two options here. Ey equal to 0 or L equal to 0. You agree with me? This one is not possible, right? L equal to 0 means my strut has 0 length. So the only way to achieve the equilibrium in a strut is the reaction perpendicular to the longitudinal direction of the strut equal to 0. So this reaction here, Ey, cannot exist in a strut. Yeah? What about dy? Well, if I do the same analysis, but now doing summation of moments about point E equal to 0, I will get the conclusion that dy needs also to be equal to 0. Yeah? So this dy cannot exist as well. So we have these two forces, dx and ex. Look at this now. Summation of forces in the x direction equal to 0. This is another equilibrium equation for the forces, right? Which forces do I have in this strut in the x direction? I have EX is positive and minus DX. They need to be equal to 0, right? To be in equilibrium. Conclusion from this is EX needs to be equal to DX and equal to the force in the strut, which we call FDE, for example. Yeah? So I can say this is not going to be DX and EX. This is going to be the same force, which is my FDE. You see what's going on in a strut? You might be thinking, why am I doing all of this? Well, the reason why I'm doing all of this is because in our problem that we are doing, we have a strut DE there. So I know that the reactions or the force that I can have in this strut needs to be a force aligned with the longitudinal direction of my strut. I will call this force FDE, which is equal to this, FDE. And if you look there, that link in blue basically is applying a tensile force in my strut DE. My strut DE will react on the link in blue with the same force but in the opposite direction. This is going to be my FDE. And I know the orientation of this FDE is the same orientation of my strut. So in point D, I only have one reaction there, FDE, which is the force in the strut. Okay? Again, I applied Newton's third law, action-reaction. What else do we have in this blue component? Well, it is said in the question that in order to release the press, there is no contact at point G. So the force at point G is going to be equal to 0. We don't have to include it there. But we need to include this force P, of course. So I need to include this force P, which is applied at this point F. All right? So this is all I have in my free body diagram in blue. Coordinate system there. All the reactions and external forces applied in my body. So I can say this is my free body diagram. And now the only thing I need to do is to build the equivalent system, force moment for this one in blue, and say that resultant of the force is equal to 0. Summation of the moments about any point you want equal to 0. Before we do that, let's go back to this body in red, because, for example, from this equation, you can get Cx, according to the calculations I have here, you should get Cx equal to minus 3.3 kilonewtons. We are working in kilonewtons. If you replace Cx in this first equation here, if you replace Cx, you should be able to get Bx. So we can also do that. And then if you do that, you get Bx equal to 3.3 kilonewtons. And then this y equation, this one here, there's nothing we can do. So we will just keep this equation, Cy plus By plus 1.2 equal to 0. We will come back to this equation. So, look at this. We got Bx positive, Bx positive means my initial orientation for my reaction Bx was correct. So I can replace here Bx with 3.3 kilonewtons. Yeah? We got Cx minus 3.3. It means my initial orientation for Cx was wrong. So what I have to do is reverse Cx. So Cx is going to be in the opposite direction, to the left, like this. And this is going to be 3.3 kilonewtons. Yeah? Careful. Don't forget the Cx in your blue. You also need to reverse this guy, otherwise you are violating Newton's third law, action-reaction. So you also need to reverse this one in blue. Instead of going to the left, it needs to go to the right, like this. And this is going to be 3.3 kilonewtons. Yeah? You see how it works, more or less? Yeah, more or less is very important because you need to practice. The more you practice, the more use it will be. This is like playing football. Yeah? You play on a Sunday, but if you don't train during the week, you go to the bench or you play it very bad and then you don't play it next Sunday. Yeah? Here is the same. If you don't study, if you don't practice, when you go and play in your exam, you'll have trouble. Yeah? So, it's a good analogy. I think it's a good analogy if you like football. So, yeah, basically my message is the more exercises you practice at home, the better. You get these mechanisms in your head very quickly. And right? So let's write the equations for this. We need to speed up a little bit. So first equilibrium equation, summation of forces in the x direction equal to 0. You tell me, what do I have in the x direction? 3.3, yeah. 3.3 kilonewtons. What else? So we need to get these angles, right? So let's go back to this figure here. Maybe not this one, maybe this one here. We need to get this angle here. Well, we have this one, which is 50 degrees. Look, this 50 degrees here is this angle here, right? This is also 50 degrees. It's the same angle, right? So we can, here we can write that this angle here, I'm going to put in green, this angle here is going to be 50 degrees. Okay? 50 degrees. We will need also the angle for this force P, so let's go back to that figure as well. So for force P, well, we have this 30 degrees. So it means this angle, this angle here is going to be 30 degrees. You agree with me? The reason is force P is perpendicular to this one, and this vertical line is perpendicular to this horizontal. So these two are perpendicular. It means the angle needs to be the same. Yeah? 30 degrees. So I can say that this angle here (30 degrees). Does it make sense? Yeah. So we have all the angles. Now let's continue. Summation of forces in the x direction. We did put there 3.3 already. So FDE is going to be positive or negative? The horizontal component of this force. You need to decompose this force in the horizontal direction. You'll get this component, right? So it's going to be positive because it has the same direction of x. And the horizontal component is FDE sine of 50 degrees. Okay, so I'm going to speed this. This is vectors, what we did at the very beginning, right? Now I have to also get the horizontal component of force P. Positive or negative? Positive is P times what? Sine of 30. That's all I have in the x direction. This needs to be equal to 0 to be in equilibrium. Next equilibrium equation is summation of forces in the y direction equal to 0. Which forces do I have in the vertical direction? Minus Cy. Minus Cy. What else? Plus or minus? Minus FDE cos of 50 degrees. What else? Plus P cosine of 30 degrees. This needs to be equal to 0 to be in equilibrium. Yeah? So I'm building the equivalent system force moment and making that equivalent system equal to 0. I'm doing everything in one go, right? Summation of moments about any point. You can choose any point. Because we are running a bit out of time, I'm going to choose the same point I have in my solutions. But the good way to study this is at home you can choose a different point for the moment. And of course you need to get the same result at the end. If you don't get, something is wrong, and then you can go back and review your calculations. This is a very good way to study, in fact. Yeah? So the point I decided to choose was point C. Okay? So these two forces at point C, they don't produce any moment. We need to have the moment produced by, let's start with force P. Okay, so one important thing, look at this figure, maybe not this one, maybe this, yeah. Look at this figure here. For the moment produced by force P about point C, look, force P is applied perpendicular to this direction, CF, yeah? Force P is perpendicular to CF. So for the moment, I just need to use this distance, right? Which is the distance in the perpendicular direction to force P. And that moment is going to be anti-clockwise. So I can say I will get P times 86. So P is unknown. That's what we want to know in the question at the end. P will be in kilonewtons. We are working with kilonewtons for the forces, yeah? So everything we calculate for the forces is going to be in kilonewtons. Now I just need to focus on the moment produced by force FDE. And what we can do is I'm going to decompose force FDE into the horizontal direction. This, we have seen this is FDE cosine of 50 degrees. And I'm going to also decompose in the vertical direction. We have seen this is FDE. Sorry, this is wrong, right? Yeah, this is sine here, right? This was a test. I wanted to see if you were paying attention. No, it was not. I'm kidding. My mistake. Cosine of 50 degrees. Yeah? So instead of working with force FDE in blue, I can work with the components in the x and y direction. Yeah? Why did I do this? Because it's easier for the moment to get the distance in the perpendicular directions. So let's start with this one here. Let's see what is the distance in the perpendicular direction. So we have a force here. We need to have this distance, right? You agree? This distance is 24, right? Yeah? Oh, you're right. Sorry. Something is wrong here. Oh, you need to take out this, right? So this makes what? 18 and half. Okay. So that's what we have to use here. So that moment is going to be anti-clockwise about C, so positive. The force is FDE, sine of 50 degrees. And the distance is, like you said, 18.5. That is the horizontal component. Now the force produced by this vertical component here is going to be negative, so I can put here minus. The force is FDE cosine of 50 degrees. I just need now to get the distance in the perpendicular direction. Sorry, I'm rushing a bit because we only have 5 minutes. So I have now this vertical component here. So I need to have this distance, right? Sorry. From here to here. This distance is 16. Yeah? Very good. So times 16. This needs to be equal to 0. Look at this now. How many unknowns do I have? Well, I have FDE, 1, force P, 2, and CY. So I can solve this system of equations, and if you do that, you get these answers. You get P equal to 0.2 kilonewtons, FDE equal to 4.44 kilonewtons, and CY equal to 3.03 kilonewtons. If you replace CY in this equation here, you get, in this equation, you get 3.03 plus BY equal to 0, which gives BY equal to minus 4.23 kilonewtons. All right, I lost you and I finished. So see you next week. Yeah.